All right, so in this video, we are going to continue our conversation on thermodynamics and go over the 4 laws of thermodynamics. So our objective in this video is to be able to describe the 4 laws of thermodynamics and identify everyday examples. So at the end of this video, you should be answering our essential question, which is what are the 4 laws of thermodynamics, in about a 1 to 2 sentence summary. So let's go ahead and get right into it. So as a reminder, when we talk about laws, these are laws of nature. These are scientific laws. They've been tested and tested and tested thousands of times, and it has always resulted in the same results. So these are just laws. These are laws of nature that just simply cannot be broken. So our first law, which is actually called the 0th law of thermodynamics, and the reason behind this is that they came up with laws 1, 2, and 3, and then realized there was a 4th law that was pretty fundamental to the other 3 laws. So they, instead of calling it the 4th law, they decided to call it the 0th law. So fun little backstory of history there. So the 0th law of thermodynamics says that 2 systems in thermal equilibrium with a 3rd system are also in thermal equilibrium with each other. So I do want to identify this term thermal equilibrium. What it basically means is that the thermal energy of the 2 systems is the same. So meaning they are really just the same temperature. That's kind of what thermal equilibrium means. So if we have an object A that's in thermal equilibrium or the same temperature as object C, and we have an object B that's also in thermal equilibrium with object C, then A and B are going to be in thermal equilibrium or the same temperature as each other as well. So it's a bit like the transitive property in math. If you recall what the transitive property means, if A equals C and B equals C, then A also equals B. So this 0th law also describes this phenomenon of how objects near each other will eventually reach thermal equilibrium. So if you've ever left a hot drink out in a cooler environment, I know I drink a lot of coffee, and when I let my coffee sit too long, it becomes room temperature, and that is because of the 0th law of thermodynamics. We're seeing this exchange of heat. The hot coffee is losing its heat to the surrounding air. So eventually the surrounding air and the hot coffee are going to become the same temperature. Moving on to the first law of thermodynamics, now that we've covered the 0th law. The first law of thermodynamics states that energy can neither be created nor destroyed. Now, this might sound very familiar to you because our first law of thermodynamics is simply our law of conservation of energy. That's all it is. States that energy in our universe cannot be created nor destroyed. It can only be transferred, just like we see the transfer of energy from our units on mechanical energy. We are now seeing how heat, which is thermal energy, can be transferred between objects as well. Now, we're going to take this one step further in this video because our first law of thermodynamics gives us this equation, which states that the change in energy is equal to the heat added to that system minus the work done by the system. So this equation is very useful to us. So we can use heat and work done by the system to calculate the overall change in energy. Keep in mind that these are all very related concepts. Heat is essentially energy. Work is an object's, or energy is simply an object's ability to do work. So our first law gives us this equation, and we will get some practice on using this equation in class time. So that is our first law of thermodynamics. Again, it is essentially the law of conservation of energy, stating that energy can neither be created nor destroyed. Now, our second law of thermodynamics introduces a new concept, which we call entropy. So our second law states that the total entropy of a system and its surroundings must increase in a spontaneous process. So I want you all to think of what spontaneous means. And that's really what we're talking about when we think of a spontaneous process that occurs in nature. So a process that would occur in nature is ice melting, for example. Ice melting does not require, especially if we leave it out in a temperature above 32 degrees Fahrenheit, we don't have to put much effort in to melt ice. It is simply going to melt on its own. Same thing happens in the reverse direction. If we freeze ice, okay, we don't have to put a lot of effort into freezing ice as long as we leave it out in a temperature that's lower than 32 degrees Fahrenheit, which is freezing temperature. So that's kind of what we mean with the spontaneous process. There's not, it just kind of happens naturally. This is an occurrence that happens naturally in nature. Now, the entropy is defined, entropy is simply a measure of disorder or randomness in the universe. So I know that kind of seems odd, but keep in mind our universe is made up of tiny particles of matter. So entropy simply describes how random those particles of matter are structured in our universe. Our variable for entropy is a capital S, and our unit of measurement for entropy is joules per Kelvin, which we represent with J/K. And finally, this second law of thermodynamics also gives us this equation. So again, our total entropy, the total change in entropy of a system and its surroundings, is simply the sum of the system and its surroundings. So it's a very simple equation, just adding two numbers together to get our total entropy. And the idea behind this law is that our total entropy, which we are calculating with this equation, and I will put this right here. Our total entropy for a spontaneous process needs to be greater than 0. It must increase. So that is another way to sum up this law here. Finally, our third law of thermodynamics is pretty cool because it introduces this topic and this idea of what we call absolute zero. So technically what the third law states is that the entropy of a system at absolute zero will be 0. But what I want you all to take away from this third law of thermodynamics is the concept of an absolute zero temperature, meaning that it is so cold that it is impossible for particles of matter to have any kinetic energy. So I wanted to depict this. You might be familiar with these kind of these particle diagrams from chemistry. But let's start off we'll use this example of water here. We know that liquid water, or water is liquid above 32 degrees Fahrenheit or 0 degrees Celsius. When we think of a liquid, right, these particles have a decent amount of kinetic energy. They can kind of slide past each other, and they take on the form of whatever container they are in. They're obviously not bouncing off the walls like a gas. They don't have that much kinetic energy as gases do, but they do have quite a bit of energy, of kinetic energy and movement in their liquid form. Now, if we were to decrease the temperature here, to 0 degrees Celsius, which is the same as 273 Kelvin, we would reach solid ice. So ice is our solid form of water. And even in ice, I know that it doesn't seem like the ice really has a lot of movement in it. It's hard for us to see with our bare eyes, but inside that crystal structure that's forming our ice, those tiny water particles are still experiencing tiny vibrations. They still have tiny amounts of kinetic energy here, even though they are in a solid form. They still have a certain amount of kinetic energy, which is kind of resulting in those vibrations of those particles when they're sitting in that structure together. So that again is at 0 degrees Celsius. Now I want you to picture these tiny, tiny particles of ice and with absolutely no motion. This is when we reach absolute zero, when these particles cannot move, they have zero kinetic energy. That is this concept of absolute zero. Now, we have estimated this cannot be achieved in nature, right? We have estimated that absolute zero would be negative 273 degrees Celsius, which is 0 Kelvin. So absolute zero, again, is when our temperature has reached 0 Kelvin, negative 273 degrees Celsius, and there is absolutely no motion in these molecules. So this would be really tragic if we reached absolute zero in our universe. This is why it cannot be achieved in nature, because our particles in matter require some kinetic energy so that we can form all of these substances that we see in our daily lives. So this would be pretty much a travesty on Earth and kind of the end of us all. So we don't really want to reach absolute zero, but there is an absolute zero that exists with objects that have absolutely zero kinetic energy at 0 Kelvin and negative 273 degrees Celsius. So that is really all that this video is going over, those 4 laws of thermodynamics. Again, keep in mind the definition of a scientific law and kind of what that means. These are statements that are governing our universe. They are laws that cannot be broken by nature. So again, please remember to write your 1 to 2 sentence summary at the end of your notes, and I look forward to discussing this with you all more in class.